it says here on this YouTube thing, this new thing, that you're legally required to comply with the West Children's Online Privacy Protection Act. The laws, you are obliged to tell us if your live stream is made for kids. It says use live control room, right? So click on live control room. Right. Well, they all stink. So yeah, get that, doesn't work. I have to do it on my phone. That sucks, isn't it? Really sucks. Crap. Yeah, useless. Yeah, I'm on XP, you see. Right, so delay lines. Earlier today I was doing some experiments and testing because it's a lot of math stuff, and we talked about microseconds and milliseconds, microseconds and nanoseconds and all this stuff, and it's very finite. Oh, my microphone's over there. It would help if I brought the microphone a bit closer, I suppose. Right, so we're talking about microseconds and nanoseconds, and yeah. So earlier today I used some jumper leads, just some cheap tiny jumper leads to connect. Basically between there, between there and there, and I stuck a capacitor on the end of the jumper leads, and guess what? We had a massive delay, which was too much of a delay. And yeah, just having a couple of jumper leads in series with a capacitor was a massive delay, and I don't want that much of a delay because it was causing huge loads of lag. The delay has to come basically at the end of the pulse cycle. Oh, actually, let me just draw it because I'm not going to start everything running right now. I'm not going to draw it in this SketchUp program, in this Design Spark program, because it's a little bit too busy to do that. So what I'm going to do is I'm just going to explain. Alright, so the waveform. Oh, what am I doing? What's happening here? Where's my control bar gone? Where are you? Two bars. A bit thicker. Oh, something like that. Oh, right, okay, right, so this is a waveform that's basically under load. Right, and it's under load, that's why I'm doing flat edges. Right, so our waveform, make sure that's going out okay. Yeah, it is a bit. Right, so basically the pulses happen right at the end of a cycle as the waveform is dropping off. So what we do is we have where's my rubber gone? So we have basically what we have to do is insert our pulse. We have to get our pulse to be timed at the end of the cycle of the waveform, which is like like this sort of thing. So, if the pulse is too early, then we lose power. Well, we're actually not really gaining much, but we need to chop the pulse, we need to chop the main generating pulse off right at the very end of the cycle, which is basically there. Now, the cycle, the time base, I should say, let's just draw a line. Text. Time. Click the wrong button. So that's our time. Now, this pulse here is literally a few microseconds or nanoseconds after the duty cycle. There's another pulse, obviously, on the other waveform, but we're just going to focus on one half the waveform right now, because by using a longer lead in series with a capacitor, right? So if we have our capacitor, right, if we have a capacitor and we have a really long lead, right, imagine this lead is 10 feet long or something, or right, then to connect to the capacitor, then that would automatically create a delay anyway because of the inductance of the wire. So by the time the electricity gets, the energy gets to the capacitor, there's a delay. So let's go back to the diagram. So what do we have? Right, so this input side, this is the input side. What we want to do is you need to store energy in this capacitor here. So it could be a bit bigger than 22 microfarad, it could be 47 or maybe, yeah, something like that. But what we need to do is store some energy in this capacitor here, because we want to deliver that energy through to our exit coil, which is L2. L2 is the exit coil, which basically delivers the pulse that we were just looking at, that small pulse. 22 microfarad of C1 is basically storing energy to deliver into the coil. But we don't want all of that energy to arrive all at the same time, because what happens is we end up with a pulse that basically, go back to this, we end up with a pulse that's discharged all in one go, basically. So it happens all at once, and we want it to last a bit longer. So we want this pulse to be a little bit longer, so that it removes as much drag as possible, but we want a nice big pulse at the end of the cycle. And I have been getting pulses about this halfway up the waveform. Basically on the this is, well, let's just draw this in a minute. Let me just draw a little line a minute. Right, this is 0 volts. This red line is 0 volts. Actually, I made my black line a bit too big, actually. Just a minute. Let's just get rid of that a minute. Right, that'll do. That'll work. So basically what happens is our pulse is basically pulsing up to the 0 volt point, which is great. It's fantastic, because that's what we want. We don't want it going the other way. We want it to be basically coming up to 0 volts, which is excellent. And I've actually been observing that. It's been very good. I've had some pretty nice pulses, but too much energy is dispersed in this small microsecond area. I would like to make it longer, so how do we do that? Right, going back to a schematic, we have this other capacitor over here, which is before L1, which basically is direct. This is all in series of the output coil, by the way. The output coil is generating power, and it's all being bypassed through this circuit here. Now, when the exit coil, when the actual generation coil actually starts to exit, we get a bit of a back EMF pulse anyway, so that kind of triggers everything happening really. It seems to be kind of magical how it happens, but it happens at the right time, which is really cool, but I need to delay it a little bit longer. So what I'm saying is, if we can store energy in this capacitor here, it'll be delivered a little bit slower through L1 to C1 and L2, which is our exit coil. So we end up with a pulse from this capacitor here, but we want to sustain that pulse as long as possible. And so what we do is we have a tap. What we do is have an adjustable tap on this coil. So we basically, I don't know if I can show you on this really, but we have a connection between here. Let me just try and draw this a minute. Add connection. Right, so we have a tap that we can move along this coil, or we could have a wiper. So we can actually advance and retard the delay through the circuit, so that basically we can deliver that energy, either advance it or retard it through the coil. And so what we should be able to do then is extend our pulse, so that our pulse is a little bit longer. That's the idea. Go back to our schematic again. Now, if I put a smaller capacitor in here, the pulse gets smaller. The actual pulse gets a lot smaller. The amplitude is lower. If I put two bigger capacitors in there, no, actually no, I'm getting it backwards. If I put two bigger capacitor at this point here, the pulse gets smaller and it gets fatter, but it's not strong enough. So basically what I'm saying is this pulse here would be about half its way up if it has a larger capacitor, but it'd be a bit wider. Well, I want the pulse to be basically coming up to 0 volts, or basically in the center. So using a larger capacitor doesn't help very much. But if I use a smaller capacitor, I get a bigger spike, but it's over a shorter period, a few milliseconds, it's over a few microseconds, right? So, how do we sustain the pulse is simply to use a capacitor before L1, so we can continue to send energy through L1 after power generation has ceased from the main generator coil. But some of that energy, some of the energy that's in C2 is going to bleed back through the circuit anyway. Not much, but because of the fact that the windings are many more, there's many more windings on the generator coil than there is on the exit coil, it shouldn't matter too much. Most of that energy is going to go through L1 anyway to charge up C1 and drive our exit coil L2. Anyway, I hope you heard what I was. Oh, is my audio on, by the way? What's the point? Testing. Yeah, it is. Just need to make sure, because I'm not talking myself. Right. Anyway, it does work, because I was doing some tests earlier with just some jumper leads, and just having a jumper lead between where this L1 is, two jumper leads actually, because they were in series. They were actually connecting a capacitor across this capacitor here. But the delay was massive, it was just too much, and so we can't even use jumper leads when testing this circuit. You can't use them because the amount of delay across the jumper leads is so great, it just, yeah, you get the idea. So it's got to be, it's very difficult to, you can't build this on a breadboard. You know, trust me, you can't build this on a breadboard because the inductance and the leads and wire lengths are critical. We talk about microseconds of delay. It literally has to be built close to the actual exit coil. It has to be very close coupled to the exit coil. So anyway, there's two ways of making L1. One is to use another coil wrapped around, that's literally one layer thick, just one wrap of wire around a piece of plastic, and using a tap that moves along that. Or I could use some circuit board and try etching the coil directly onto the circuit board, which is probably what I was going to try, because it might be a lot neater, but I don't know. You see, the thing about the coil idea is if you cut the wire accidentally, you know, if you move it back and forth too many times and you cut the wire, you're in shit, you've got to make another one. So, at least, and also with a circuit board type, you can actually tin it and make the coil thicker if you want to reduce its impedance, so that it's actually, you can tune it just by adding solder to it as well, which is a lot easier than messing about trying to, you can't exactly solder the wire onto a coil that's wrapped tightly together, because you'll join all the wires together, so that's not a good idea either. Yeah, so we're only talking about a few microseconds on this coil. So it doesn't need to be massive. Got such a big difference by changing between 22 microfarads at this point here and 47. Putting 100 microfarads on here made everything slow down a lot. It just really lagged because the pulse was just non-existent really, and there was loads of drag. But I got good results between about 10 microfarads and 22 microfarads. So the sweet spot is in between 22 and 10 really, because this is actually in series with two of these L2 coils. This 22 is actually in series, in parallel, sorry. It's in parallel with two L2 coils really. So when I'm actually using L2 as a single reference point, but there's actually two exit coils there, not just one. That's the difference. So anyway, I thought I'd explain it, because I know there's a lot of people that don't understand how you make a delay line, but a delay line is simply an inductor that takes a few microseconds to react to the input. And so when a voltage comes in, the inductor basically isn't conducting anything for a few microseconds, and then the voltage comes out. It's the opposite to a capacitor. When you push power through a capacitor, you instantaneously push power out of it, and then it drops off rapidly afterwards. But an inductor works the other way around. You send a voltage through an inductor, and you've got nothing coming out the other end for a few microseconds, and it comes out. That's how it works. It's a delay thing. Yeah. Right. So basically, I want to have extra power stored to deliver. Now, there is a possibility that I could have a 3-stage inductor circuit. Oh, what we're doing, I've got the wrong one on. Undo that. Just push the escape. So if I select that and move that over a bit, oops. So I could have another L here, in between here and there, and another capacitor on this end to create an even bigger delay. That's what I wanted to explain. So let me just drag that over there a bit. Oh, that's moved now. Don't need to worry too much. Now, if I copy that and remove that and paste this one here, right? So we could two L's there and even another capacitor over here. So you could create a bigger delay. So what happens is, you've got power coming in, there's a delay. Charges the capacitor, there's a delay. Goes through the coil, charges the capacitor. So this is a two-step delay. This might be too much, but still, it's an option I'm going to put on the board, on this circuit board I'm going to do. Might as well bring that in a bit actually. Anyway, I need to move that back a bit now. So, imagine that was a wiper on a pot. Same principle, except it's a tap, or it could be a wiper even if you've got a coil on a bobbin where you could... The old TVs years ago used to have carbon wire with a slider that you would slide along. Or even coils can be done like that, just the same principle really. You could use a coil, a copper wire instead of carbon wire as a tap point to move the tap in, to adjust it so it becomes a variable inductor instead of a variable resistor. But you know, you go and look up variable inductor, you'll never find one. I wonder why. I wonder what they're trying to keep hidden from us. But you can make one, you can design one yourself. I mean, it's not a complicated thing to make, really. Right. So, yeah, that's all I wanted to put into a video to explain. I mean, you could, for lower frequencies, for much bigger delays, you could simply have a resistor there, a variable resistor, and a variable resistor there instead of a coil for massive delays. You know, we talk about seconds or much bigger delays. But we don't want big delays for this because, yeah, everything happens so quick. So, yeah. Anyway, I think that's all I've got right now. So, thanks for watching.